Welcome to my Pixie presentations. Pixie is a full-featured 2D graphics library for Nim. You can install Pixie with simple nimble install Pixie and view the source code on GitHub treeform/Pixie. Pixie is a collaborative effort between Guzba and me, Treeform. Why did we do it? Why not just use Cairo or Skia? So there's several reasons behind that. First off, Cairo and Skia are written in Nim, and we really like Nim and we want to use it for everything. Second, the best way to learn something is to do it. Before starting with Pixie, I thought I knew how graphics and how vector graphics works. But I didn't know at all. After doing Pixie, I've learned so much more how vector graphics work and how they do. And I got to use Nim. Nim is excellent and has a lot of cool properties. Also, Cairo Text API isn't that great. And Skia, being C++, is kind of hard to compile in your projects. Pixie is a top-level library based on a lot of smaller libraries that we have written. We have the Benchy library used for benchmark. We have the Bumpy library used for intersections and collisions. We have the Chroma library used for colors. We have the Flatty library used for flattening data structures and serializing them. We have the VMath library for vector math. We have the NimSimD library for SimD. And then we also have Zippy library for compressions, mainly used in the PNG file format. At its core, Pixie is all about grids and grids of pixels. And those pixels contains colors inside. Just RGBA colors, as you would be used to in other stuff. All the colors are coming from the Chroma library. Path filling. One of the most important things in vector graphics is the ability to fill paths. Like the star here. How would you go about filling it a solid color? Well, you put it on a pixel grid and then you do a ray scan. You start with the ray and then you go till you hit something. Hit one of the edges of your path. After you hit something, you know that you are now inside the path. So you travel with your ray, again, this time filling the pixels until you hit another collision. Once you hit another collision, you can travel all the way to the end. And that's how you fill a single row. And you just repeat that for multiple rows. How do we do anti-aliasing? Well, for anti-aliasing, we just fire multiple rays and then average them out. You did anti-aliasing to get those nice, smooth edges. What are vector paths? So in the SVG language, vector paths are defined this way, and we mainly use it in Pixie as well. The first command is a move command, move to 1010. The second command is the L2020 command, which means line to 2020. Here's a more complicated path commands for our star shape. So it starts out with the move command, it moves somewhere onto the star, and then next we have the curve command. The curve command defines the control point that describes the curve. So we go over the curves. The next thing is the line command. It just moves the line. And you can draw the entire path just with move, curve commands, and line commands. It's pretty simple. Well, except the curves. So we don't like curves. They're very hard to deal with and hard to intersect with. What we do instead is we discretize the curves into lines or line segments. The way we do it is first we take the curve and we split it into two. And then we see if the error rate is enough to stop. If it isn't, we continue, we subdivide it again and again and again till the error rate is acceptable. One other important aspect is the winding rule, the direction with which the line segments move. So when you hit a line segment going up, you usually want to press add 1, and then you draw because you are 1 until you hit a curve going the other way, which makes it -1. This is called the non-zero rule. You can follow the non-zero fully here, and you can see the various fills happened with the rule. So first we hit it, we set the pen to 1 because we went up. Then we actually subtract from the pen winding rule because we are going down, and so the pen winding rule was 0. Then we move a little bit and we hit a line that was going up. So we add 1, so now we fill because the pen is non-zero. And then we hit a line going down, and so we set the pen rule to 0, which is non-zero, so we don't draw. That's how the non-zero rule works. There's another rule called the even-odd rule, which draws everything when something is even. So in this case, you can see we hit the 1, and then we go up, and then we go up again, and we set the pen to 2, but because 2 isn't even, we actually don't draw anything in there. We would actually draw something if this was the non-zero rule, but because this is the even-odd rule, we don't draw the 2. And then we hit the path going down, we set it back to 1, which we draw, and then we had another path going down, which sets it to 0, which means we don't draw again. The even, odd, and not zero rule is very important. The mistakes usually look like this. If you don't get it right, you get some sort of weird cutouts in your paths. So usually, if you have a path, you need to know how it was filled. Either it follows the even, odd rule or non-zero rule. And you gotta support both. Text is hard. Yeah. Before starting this, I thought text going to be easy. No, it's not easy at all. There's so much to text. Well, the easy things is that texts are just paths. They just have to be filled and put into pixels. Not that hard. We've just done that with the star shape. Next, we have to understand what is called the font metrics. Like, how do these glyphs fit on a line? So with the glyph, we usually have the baseline. We have the ascender, which is like the height from the baseline to the top. And then we have the descender, which is the baseline to the bottom of the glyph. And then together, the ascender and the descender make up line height. Knowing these properties, we can position the glyphs next to each other. Next, we have kerning. Kerning is also kind of hard to get right. It's very easy to see when you have wrong kerning. You can see that the text doesn't really line up. It looks kind of weird. Yeah, and that is what you usually get with bad kerning. To do the correct kerning, you have to parse a bunch of kerning tables and a bunch of font metrics to make sure everything line up to get the font kerning that the designer intended. Kerning is just the space between the letters, but it is very hard to get right, and you usually have to follow what the type designer intended for the font to look correct. The next thing we have in Pixie that a lot of other vector graphics libraries don't have is spans. That is the ability to typeset different runs of text. So either with different fonts, different colors, and even different italicized or bold. We support that by creating a bunch of spans and then typesetting them. And we even support wrapping on the spans. It's great. We spend a lot of time working on the text to get it right. Speaking of getting things right, it is very, very important to have a big test suite for your graphics library. It's almost impossible to have a graphics library, a good graphics library without a large test suite. And so we do extensive testing in our library as well. So one thing we do is we call the X-ray Diff viewer. So what this allows us to do is to take the master image we generate from a vector graphics program, in our case that is Figma, and we compare it to the vector graphics that we draw. And you can see sometimes we are dead on, like with the first line, verb with object, we are completely the same. But then we have a little anti-aliasing differences with Starlow. We actually think that we have better anti-aliasing at Figma at this point, and that's why there is a difference. And then for the last two sets of text, the Starlow and the description, we are slightly still off, but we are working hard to match it. But you can see we're pretty close. The characters are all end up nearly in the same place. Without this X-ray diff viewer, you would not be able to tell that something is off. And that's why we use the diff viewer, is because even the most minute differences are easily seen with it. Here you can see an example where there's no difference. We are drawing a transparent image exactly the way Figma is drawing it. So this is great. Here's the Diff viewer for the tiger. Tiger is a very complex benchmark and is used in a lot of vector graphics programs to benchmark them. So here you can see how well we draw the tiger compared to Figma. And you can see there are some anti-aliasing differences. I will zoom in on the mouth of the tiger. You can kind of see the pixels that are different. And you can see they're always at the edge and they're always just a little bit different. Just looking at the images, you will not be able to tell that there's any difference. You need an X-ray viewer to tell the microscopic differences between the anti-aliasing. And we believe our anti-aliasing is just better. There's a lot of optimizations you can do in vector graphics. One big example that we do is what we call Uber draw. So here's the idea: is we have a draw function which draws an image A onto the image B, and we can actually draw it, but there's a lot of optimizations that can be done. For instance, if the image isn't scaled or rotated, or doesn't have fractional translation components, which actually happens a lot, we can draw it really, really easily. If it's not blended, meaning we don't care about blending between the pixels above and below, it is even faster. Here's an example. Here's an example of pixel aligned image. You can see that we can actually just do basically a memory copy of images from the above image to the image that is below. But if it's not pixel aligned or has scale rotation, we actually have to do a lot more work to blend in the pixels and apply all these transformations. So using another tool called Benchy, we can benchmark the performance. You can never guess where the performance is in your code. I'm always surprised by the slow parts. Like, I thought after working with performance stuff for so long, it'll be easy to see where the performance bottlenecks are. No, there's no way to see without benchmarking things first. And here you can see that we have the draw correct, which does the very complicated or naive way of drawing blended, shifted, rotated images on top of each other. You can see how slow it can be. Or you can see like the draw Uber, which detects cases, like good cases where we can actually apply the optimizations. You can see how much faster we can get. We're like thousands of times faster here. It is great. And yeah, and we apply these kind of benchmarks to many of our operations to get them fast. I usually prefer in these benchmarks to look at minimum time rather than average time. Most benchmarks look at average time, but I like minimum time, and here's why. So during the minimum time, there's all these like events that can happen during a runtime of your benchmark. Like there's just an awkward cache miss that happened. There was maybe a random GC pause that happened, or even an operating system task switch. So you can't really account for these things very well in your tests. So what happens is you basically average this in, cache misses and GC pauses and task switches into your run. But the minimum run will probably contain the run where none of these has happened, unless you're like really stressing the cache. Like you might just kind of not have these kind of big events that mess up your run. So that's why I like looking at the minimum run, because it's usually more stable and easier to reason about, rather than the average run where you can have a bunch of these things kind of creep up. But I still don't want to dismiss the average entirely. I think average and standard deviation is very important to not see things that aren't there. So a great example of this is when you're benchmarking something and you keep rerunning and rerunning the test and you see numbers getting better and better and better, but then they get worse for no reason whatsoever. A lot of time it is just random noise, and that's why I think it's very important to look at the standard deviation to see if you're within the noise. If the previous result is within one standard deviation of your current result, you probably didn't do any change and you're just looking at noise. So once you are one standard deviation away from like where you were, you probably got into the noise, and it's going to be very hard to see something to optimize. And you should probably try a different approach. How to use Benchy. So this is very important. We use Benchy with this little time it macro, and then you do your operations. But it's very important to keep the keep macro as well. The keep macro just takes any type and make sure the compiler doesn't optimize it out. The compiler loves to optimize stuff out. A lot of my time running the benchmark, I get like the time it took was 0 seconds, but I know it didn't take 0 seconds. I know that the compiler just optimized something out. So it is very important to actually test the things that you think you're testing. I see a lot of people just running your code and looking at the time. That's not enough. Compilers will optimize your things. You need to look at the minimum run and you need to look at the standard deviation. And we do all that while developing Pixie. Another cool optimizations that you can do is what we call, I guess, the memory grain. So a naive way to loop over the image is to first go into the x coordinate and then go into the y coordinate. It makes sense, it's natural. So this is the way you would write the loop for x, from 0 to width, for y from 0 to height, right? But that actually goes against the memory grain and you're jumping all around the memory. Because usually the images are stored in rows and the y's are stored in columns. And what you are looking here is a column at the time. It is actually much faster to flip the for loop into kind of slightly in a natural way for y for x. But this way, you're traveling with the grain. You're traveling with the cache lines of the memory. And you actually get much faster results. And here they are in Benchy. Using for x for y loop is slower, and using for y for x loop is like almost 3 times faster. It is fantastic. While optimizing and benchmarking things, you should always keep in mind that there's this memory grain that you're working against, and that has basically helped a lot to optimize many of the operations in Pixie. Another great optimization example is blurs and shadows. Modern UIs have tons of shadows in them, and blurs are just like higher level shadow construct. So here we have a blur of a white rectangle, and you could do a very naive blur where you look at every pixel and you look at every pixel around it and then you blur. That is extremely slow. A smarter way is to actually decompose the blur. First, blur in the x direction, and then take this image and blur it in the y direction. And that actually speeds up your operations a lot. But you can see that the blur in the x direction actually goes with the memory grain, but the blur in the y direction blurs it in columns, which is really bad. So it's actually cheaper to translate it in 90 degrees and do the blur again, kind of like in this rotated x direction, but really in the y direction, and actually reap the benefits of going with the memory grain. Even though you do a whole 90-degree copy operation, it still ends up being much faster. And then you just have to rotate it back to 90 degree to get the correct blur. It is so much faster. Check this out. Like the blur slower, which does the decompose blur in the x direction and then the y direction, is whole 2.5 seconds. But if you rotated, even with the rotation like operations, you have to rotate it once and then rotate it back. Even with those operations added on, doing the scan in the basically with the memory grain pays so much dividends. Check it out. Just 300 milliseconds to do the blur, and yeah. And there's a lot of operations that we've done this way. Another optimizations that we do is using SIMD. SIMD is really weird. It's like you can go faster using the strange CPU instructions. We use the excellent NimSIMD library for this. Yeah, it's almost like programming magic. You do these like voodoo instructions to make your code go faster. It's really strange. Here's an example of how you would do SIMD. So in the first loop, we just have a simple loop. We're adding up a bunch of coverages. Yeah, it looks pretty simple, but you can actually do this loop kind of like, instead of doing one coverage addition at a time, you can do 16 coverage additions at a time, and this is what the loop does on the bottom. It loads the stuff 16 times and then it adds stuff 16 times and then stores it. So if you don't have operations that you can parallelize like this, SIMD probably won't help you much, but in graphics we have a bunch of parallel operations like this, so SIMD helps us out a ton. Here's an example for SIMD doing invert. Invert is when you take a color and you just flip them. So here is how you do an invert using non-SIMD is you actually you read the pixel, you invert the pixel, and then you write it back. That's basically the basic invert here, but you're just doing the thing one at a time, just one pixel at a time. But you can actually do SimDiv with 4 pixels at a time or 16 values at the time. So yeah, the loop ends up being we load 4 pixels in at once, we do the operation on it, and then we store it. So yeah, it's ends up going much faster using SimD. Yeah, so SimD versus memory. So that's like the big thing with SimD is you're trying to do more efficient memory write. By doing more per cycle, you can make better use of the memory read and write bandwidth. That is basically what you're trying to strive towards. When you use SimD, you're striving to this goal to basically eliminate all the wait time in the CPU and basically go as fast as the memory will allow you to go. Yeah, and so that's what we try to do with all of our SimD operations. Just stop being CPU bound and become memory bound. Again, here's the benchmark with the with the color inversion. You can see that with SimD we're way faster, just 2 milliseconds to invert a huge image, but without SimD it takes 12 milliseconds. Yeah, SimD can really speed up your operations. Here's a very different way to speed things up, is to actually use a completely different representation of data. Usually when you deal with graphics, you're dealing with RGBA straight color, which means that RGB and A values can have any value in the range. While we with Pixie use a different type called RGBX, which stands for Premultiplied color. So in RGBX, the alpha value has been already applied to the RG and B components, which means that RG and B components can never be greater than the A. But these colors are actually the same. Premultiplied alpha allows greater speedups because it removes a bunch of divisions during blending operations, and a bunch of graphic operations are just blending operations. So this ends up being a lot faster. But you usually don't have to deal with this if you're working with Pixie. Most of the time it is handled for you automatically. So when you read a PNG with Pixie, we convert it to a premultiplied alpha color. Then if you're going to do a bunch of operations with the color or with the image, we do handle all premultiplied alpha things inside, because it's very fast to do the premultiplied alpha. And then if you write the image, we just write it back as straight alpha. Yeah. If you're going to like take a Pixie into a texture, you might have to think a little bit about premultiplied alpha, but usually it's pretty easy to deal with. But it just reaps the benefits of the premultiplied alpha are great. It drastically speeds stuff up. It is basically required to do any SimD operations. It's very difficult to do integer divisions in SimD, so a lot of times SimD would not be possible without using premultiplied colors. It's great for the CPU, and it's pretty much critical for SimD and things. So that's why Pixie uses premultiplied alpha. Another big thing that we wanted to do in Pixie is the API. We wanted to make it easy, and we actually achieved it. So the Pixie's context API is heavily inspired by the HTML canvas API. In fact, here's how you draw just a red rectangle on a screen with JavaScript, really easy. And here's how you do it with Nim. Yep, that's right. We just removed the semicolons. In fact, you could probably just keep the semicolons and keep the code exactly the same. So there's tons of tutorials on how to use the HTML Canvas API. There's tons of explanations, and you can just basically copy paste them into Pixie and they will work. We support large amount of the Canvas API. You don't believe us? Here's a more complicated example. Again, this is in JavaScript. You see we have a bunch of line width and strokes and fills, and we fill the paths. You know, kind of a complicated example. Again, translate this to Nim. just remove the semicons. The API is nearly identical to the JavaScript ones. So any code that you had using Canvas or any code you can find online that uses Canvas will probably work pretty easily in Pixie. The Cairo API also inspired the context API, so if you have any Cairo or Skia code laying around from C or C++, it would not be just a single copy-paste, but it'll be a pretty straightforward translation as well, because all of the vector graphics APIs are kind of similar to each other, and Pixie is no different. The grade API is only possible due to NIM's converters. We actually use NIM converters a lot, but they can be quite dangerous. So if you are relying on the converters, you might result in code where it like converts to one type, then to the other type, then to the other type. The invisible conversions are something to watch out for, but I think they are greatly outweighed by the flexibility of the API. It just creates very good, very ergonomic API, and we like it. Yeah, the converters allow us to basically set color to all these different things. You can either use the string red, which will parse into the red color. You can either use the HTML FF000 for red, and we'll parse that. Or you can use basically Pixie's float point color, or you can use RGBA color. It all just matches and all just works. Another thing that we like, kind of similar to the converters, are the union types. So here we have the path written out in SVG language, and you can just pass that string path to us and we'll fill and stroke it. But you can also use our own like path construct. You can create a path and you can, run the move to and the line to commands directly, and you can close the path and then you can pass that path to us. Everything just works. It's really cool how NIM APIs can be very flexible and nice to use. The same thing with the union types for color types. We support a lot of different colors from Chroma, including HSV and HSL and a bunch of other ones. Like there's like 12 different color types you can use. It's great. They all work in Pixie automatically. We can also union type for paints. Paints can be a very complicated object where you define it, or it can be one of the colors that you saw before. Paints can be basically a solid, which is solid color of almost any type. But they can also be an image, which is filled, fit, cropped, tiled, or it can be like one of the gradients as well. Linear, radial gradients, diamond gradients, like angular gradients. We support all of these things. Pixie supports a variety of important image file formats. So the main format we support is the PNG. We actually use the Zippy library for that, and that is entirely written in NIM. We also support the JPEG file format and bitmap file format and GIF. And then there's the SVG. Most graphics libraries don't support the SVG file format because it is very complicated. Basically, any SVG file is also an HTML file because you can embed HTML, JavaScript, and CSS in SVG. We don't support nearly that much. We support enough SVGs to draw icons and images you can find online, but we don't support the full format because it's just massive. We also support many font file formats as well, such as TTF, TrueType file format, or OTF, OpenType file format. Actually, TTF and OTF are very similar. It is basically the same file format with extensions, so we support both. We don't support some of the things in OTF because, again, it is a very large format. We also support a lesser known font file format, again, called SVG. They're just fonts embedded in SVG. We support that as well. It's a very easy font file format to work with if you want to generate fonts. SVG format is the way to go. We also have this cool thing called Pixie/demo. You can just import that, and that gives you little windowing and input abilities to draw. Just, gives you a quick window to draw stuff in. And you can do this for tests and examples and all kinds of stuff. If you're making a full-fledged applications, I recommend maybe looking at how we did it in Pixie demo. But this is just for quick things to kind of get something shown on screen. Very easy to use, just like little demos. If you want to use Pixie with something more advanced like SDL. We have examples for that, how to integrate Pixie with SDL. We also have examples how to integrate it with GLFW. We can also have example with Glut. That's kind of the old OpenGL demo thingy. And then we also have examples how to just use Pixie with straight Win32 API, no OpenGL required. Again, very easy. The examples are in the repo. Again, you can install Pixie with Nimble, just Nimble install. All the code is open source under the MIT license. You can find it on GitHub, treeform/Pixie. And it's a joint collaboration between Guzma and me, Treeform. Thank you very much.